I'm fairly confident that most of Chapter 5 you will find is revision. There's really only one concept that we include in this chapter that is exclusive to Extension 1, and it is possibly a concept you haven't seen before. But really, it's just an extension of the midpoint formula. But we'll see that when we come to it. So this chapter covers distance formula, which I'm sure you've done, midpoint formula that I was just talking about, and we see an extension of that. The gradient formula, equation of a straight line. Now you've been able to tell me that already. Lines that are parallel, lines that are perpendicular, intersections of lines. Well, we've talked about the intersection of graphs, more than just straight lines. Perpendicular distance, that could be also a formula you may not have come across. Angles between two lines, possibly, though some of you will. And this one is certainly the extension concept that you most probably haven't touched on before, but like I said, it's based on the midpoint formula. Close connection there between those two. So, of course, this isn't going to be just like the stage 5 chapters you would have done on this concept. There's going to be more difficult questions. And they're going to be the actual application of these concepts, the applications. So what situations require us to use the distance formula? What applications could there be that talk about the midpoint or lines being parallel and perpendicular? Many of the questions are going to be worded questions because you know these formulas, you know how to substitute into the formula, you've got that skill, you've already developed that skill, been introduced to that skill. Now it's taking that skill to the next level and not necessarily being told to use the particular formula in this situation, but being given a situation, you have to be able to make the connection back to a formula. You'll hear me talk lots about connections throughout this chapter because that is very much the style of the question, that you're not directed towards doing a particular mathematical process. You have to know that from reading the question, the mathematical process to choose. This is a concept that's not only come across here in this chapter, but you'll come across it throughout the rest of the course. I tend to think of this aspect of maths as the more mature aspect, maturing into the maths, realising that, yes, you will be taught skills, but it's the next level is to be able to use those skills in situations where you're not necessarily told which skill will be required. So it's thinking about the maths on a higher level, in a more mature way, realising that these math skills that you have learnt, and yes, you'll go on to learn some more, actually have practical applications. Now, this chapter lends itself very nicely to this concept because we develop graphical pictures of the concept. So you probably know already the distance formula, and in fact I think it's given on the formula sheet. And the very fact that it's given on the formula sheet suggests that the emphasis no longer is on actually being able to work the formula, that's just a given that you can substitute into a formula. You can be careful. You know what the terms in the formula represent. It's not so much that anymore. It is, do you have another understanding of that formula? At least do you know graphically what that formula is doing? So if we're talking about the distance between 2 points, it's not too difficult to realise that we've got a number plane, we've got point, it might be called x1, y1, we've got second point, it's probably referred to as x2, y2, and hope these are not unfamiliar with you. And for some reason, we want to know the distance between those 2 points. We can represent the situation graphically, and you will rarely ever approach a topic where you don't connect your graphical understanding of what's going on back to your algebraic understanding, and the algebraic understanding of the distance formula is the distance between 2 points x1, y1 is x2 minus x1 all in the bracket squared, y2 minus y1 all in the bracket squared. But like I've just said, this formula is given on the formula sheet. The emphasis is not going to be on just your ability to manipulate this formula. It's going to be understanding the graphical representation and extending on to a problem-like situation, and knowing that in this problem we actually need, for example, this distance formula, or we might need the midpoint, or we might need to rely on the gradient formula. So I think if at the beginning we know our focus is on more than just the formulas and being able to use them, and the fact that, like I said before, that they're given on the formula sheet suggests that this is no longer the focus. It'll be on these other applications of these formulas. So we need to understand thoroughly what distance is doing. Not just understand a formula, understand it graphically. Then think about practical applications. And because practical applications might start to talk about actual shapes, like a trapezium, a parallelogram, a rhombus, rectangle, or square, then you have to know the definitions of these. And again, I guess I'm not sure of how well you know these definitions, so I've included the definitions here. A trapezium is a quadrilateral four-sided figure. That's all quadrilateral means, where one pair of opposite sides is parallel. Now, parallel, that all will, by the end of this chapter, when you read parallel, you will be thinking gradient. Why? Because two parallel lines have the same gradient. That's what parallel means. They have the same gradient. So you'll be reading this word somewhere in a problem, and you will refer that back to your gradient formula, or maybe your idea that these two lines are straight lines are graphed on a number line and they are parallel. Parallelogram is a quadrilateral four-sided figure. Both, we've got two pairs, and the opposite, have to be opposite obviously, sides in a parallelogram are parallel. A rhombus is a parallelogram with adjacent sides equal in length. What's the length? Equal length. What's that got to do with any of these concepts that we have learned a process for? Well, length is the same as distance. So the distance between the 2 points or vertices of the rhombus are equal, any 2 vertices. So I take, now this being my rhombus, because this side is equal to that side in length, I know this distance, A to B, is equal to the distance, so A to B distance is equal to B to C distance. These are features you have used, however, you may not have used them in association with this actual formula. But this is what we're developing. This is you becoming, seeing maths in a more mature way. Rectangle, we've got a right angle. And if one angle's a right angle, then we see that all angles are right angles in a rectangle. Right angle. What associations are you making with right angles? Well, right angles, hopefully you realise, is this. You might take that on to be perpendicular. This shape is perpendicular, and perpendicular is something to do with gradients. Gradient of one is minus 1 over the gradient of the other one. So the gradient of 2, and so we're using our gradient formula. The moment we start talking about right angles, perpendiculars, even parallel gradients, the gradient formula will come to mind. A square is both a rectangle and a rhombus. There are some tests also associated with these shapes, and I've listed them here. I'm not going to go through them in this video. They're listed here. I'm sure that what you will do is, if you're unsure of what makes something a parallelogram, if you're instructed to show that this shape is a parallelogram, you're probably, unless you know these already, you're probably going to come back and refer to these. If you have to refer to these properties of a parallelogram, that's a sign that you haven't learnt them and it's time to learn them. I'm not going to read them out to you. You're capable of reading them. Likewise, a rhombus and a rectangle. Now, in exercise 5A, we're just talking about points and intervals. What's an interval? An interval, it has a definite starting point and finishing point. And that's why it's associated with points. That's the definition of an interval. It has a definite starting point and a definite finishing point. We've got other things. We've got other aspects of geometry that are defined as. Clearly, this is a point. When we come to our coordinate geometry, we assign a coordinate, and we call it x, y, to that point. And clearly that's a point. We have a ray. An array begins with a point and it goes in a certain direction indefinitely, forever. That's a ray. We have a line which might go through this point and it extends in both directions indefinitely, and it goes through a point. And that's what a line is defined as. Then we have the concept of an interval. And an interval has a definite starting point and a finishing point. And this is often where our x1, y1 and x2, y2 come in, because this is an interval. So you will probably hear me refer to it as a line, which is actually incorrect. It's an interval. We've got a formula based on Pythagoras' theorem for finding the distance between 2 points, or the length of an interval. What are the applications of this? In showing that a point lies on a circle, then we might use this concept of an interval. If a question talks length, dimensions, or equidistant, we'll also use that formula.